Hello there, and welcome back to the Sleepy Professor. This is your gentle space where curiosity takes its time, where science speaks softly enough for dreams to hear, and where every question is worth exploring at the pace that feels right. I'm so glad you're here with me tonight. Before we embark on tonight's journey through the cosmos, I'd love to invite you to become part of our growing community. If you enjoy exploring the universe at this gentle, unhurried pace, please hit that subscribe button and ring the notification bell too, so you never miss an adventure. Think of it as leaving a light on for yourself, a reminder that there's always a place here for wonder and rest. And if tonight's exploration resonates with you, if it helps you drift or dream or simply slow down for a moment, a like would mean the world to me. Truly, it helps keep this quiet corner of the internet alive. I'd also love to hear your thoughts in the comments. What fascinates you most about space travel? What questions keep you wondering as you look up at the night sky? Do you ever imagine what it would feel like to float among the stars? Share your thoughts. I read every single one. Tonight, we're venturing into a question that hums beneath every launch countdown, every glimpse of a starlit sky, and every heartbeat that has ever wondered what lies beyond our blue horizon. How fast can we truly travel in space right now? Not in theory, not in dreams, but in this very moment, with the technology we've built with our own hands. It's a question that sounds simple at first, doesn't it? Almost mechanical, like asking how fast a car can go, or how quickly a plane can cross an ocean. But behind this question hides something far more profound, the story of movement itself, of how we measure speed when the road disappears beneath us, what it means to move through something so vast, so empty, that motion begins to lose its everyday meaning. Before we start drifting too far into the depths of space, let me ask you something. Where are you listening from tonight? Take a moment and think about it. Maybe you're curled up somewhere quiet, perhaps in a city washed in the hum of late lights, where the glow never quite fades, or somewhere rural, where the night sky is generous with stars, where you can see the Milky Way stretching across the darkness like spilled milk on velvet. Maybe you're in bed, lights dimmed, ready to let these words carry you towards sleep. Or maybe you're traveling yourself, on a train, in a car, moving through space in your own small way. Wherever you are, I want you to know something remarkable. There's a kind of motion around you already. Motion you can't feel. Motion your body has learned to ignore completely, but motion that's absolutely undeniably real. The earth beneath you is spinning. Right now, at this very moment, as you listen to these words, you're moving at nearly 1,000 miles per hour. Picture that, 1,000 miles per hour. That's faster than the speed of sound, faster than any jet fighter, and you're doing it without even trying, without even noticing. That same Earth, that spinning globe we call home, is also circling the sun, not slowly, not gently, but at over 67,000 miles per hour. Think about that for a moment. Really let it sink in. 67,000 miles per hour. If you could somehow stand still in space and watch Earth go by, it would be a blur, a streak of blue and green and white racing past faster than anything you've ever seen. And the sun itself, our star, that brilliant ball of light that warms our days, it's orbiting the center of our galaxy at 500,000 miles per hour. The entire solar system, all the planets, all the asteroids, all the comets, everything we've ever known, is being carried along in this grand cosmic dance. And the galaxy, well, it's gliding through the universe at even higher speeds, though there's no true reference point anymore to say what higher even means. You are right now, in this moment, one of the fastest travelers in the cosmos, and you haven't moved a single muscle. You haven't taken a single step. You've just been existing, breathing, listening, and yet you're hurtling through the void at speeds that would make any rocket engineer weep with envy. That's the first quiet truth of space travel, and it's a truth worth sitting with for a moment. Even when we think we're standing still, even when we're resting, sleeping, dreaming, we're hurtling through the void at staggering speeds. We live in motion, but we rarely feel it. Gravity holds us close. Like a gentle hand, the air moves with us, sharing our journey. Everything nearby, every tree, every building, every person shares the same invisible ride. The only way to truly sense that speed is to step outside our cradle, to push against the air, against gravity, against the comfortable limits of what engines and imagination can do together. That's where our story really begins. That's where the numbers start to matter. That's where human ingenuity meets the infinite. If you find calm in these thoughts, if the gentle collision of science and stillness helps you drift, dream, or simply slow down, I'd be deeply grateful if you'd like this video and maybe subscribe. It helps this space stay alive. It helps keep this quiet place for wonder and rest available for everyone who needs it. Now, let's take a slow breath together, in through your nose, filling your lungs completely, and out through your mouth, letting everything go. Let's begin our journey. The poetry of motion. Imagine for a moment looking up at the stars, not as distant points of light, beautiful but unreachable, but as destinations, actual places you might one day reach, places with surfaces you could touch, atmospheres you could study, mysteries you could unravel. The human mind wasn't built to grasp cosmic distances easily. Evolution shaped our brains to understand the length of a football field, the span of a mountain, the distance to the horizon, maybe even the curve of the planet from space, if we've been fortunate enough to see photographs. But light years? Millions of miles per hour? Billions of kilometers? Those numbers slip through the fingers of intuition like water through a sieve. They're too big, too abstract, too divorced from our daily experience. We can say them, we can write them down, but truly understanding them, that's another matter entirely. So tonight, we won't rush. We won't try to cram the universe into bite-sized pieces. We'll take it one layer at a time, as if stepping gently through the gears of the universe. One concept, one speed, one revelation at a time, because that's how real understanding happens. Slowly, patiently, with time to breathe between the big ideas. Speed in its simplest form is a relationship between distance and time. It's math, yes, but it's also something more fundamental, how far something moves and how long it takes to get there. On Earth, that idea is almost comforting. Cars, trains, planes, we can measure their speed against a map, feel it in the rumble beneath our feet or the tilt of a window view. We have context, we have comparison, we have the ground rushing past to remind us we're moving. But in space, all that context vanishes. There's no wind whistling past the windows, no sound of engines that you can hear from outside, no passing scenery, no landmarks, no signs saying you're halfway there. There's only emptiness and acceleration. The feeling of speed fades, replaced by the still hum of inertia, the silence of momentum. Astronauts often say that once you're in orbit, it doesn't feel like motion at all. The world spins below you, continents and oceans rotating past the window like a slowly turning globe. But the cabin around you is calm, silent, steady. You're moving at 17,500 miles per hour, racing around the planet faster than anything humans ever built before the space age. Yet it feels like floating, like being suspended in honey, like time itself has slowed down. That contrast between the numbers and the sensation captures the strange poetry of space travel. The faster we go, the less we feel it. The more energy we burn, the quieter the universe seems to become. It's counterintuitive, it defies our expectations, and yet it's true. And yet, despite this paradox, Every mission that's left Earth is a small rebellion against stillness. Every launch is a declaration. Every spacecraft is a promise. We will not stay put. We will not accept the limits of our cradle. We will push. We will explore. We will see what lies beyond. When early astronomers watched planets move across the night sky, they imagined perfect spheres gliding across celestial crystal, beautiful, elegant, and completely wrong, but beautiful nonetheless. When Newton described motion, he gave us the language to calculate it. He showed us that the same force that makes an apple fall also keeps the moon in orbit. When Einstein came along, he reminded us that speed itself has a ceiling, that as we approach the speed of light, time and space begin to warp, bending the rules of perception and physics alike. Somewhere in that complex tangle of theory and wonder lies the story of our speed. Somewhere in those equations and observations and experimental results is the map that shows us how fast we can go and what it costs to get there. And here we are now, in this quiet present, asking how fast we can travel, not as a mathematical exercise, though the math is fascinating, not as a technical challenge, though the engineering is extraordinary, but as a measure of how far imagination can reach when it's given tools to work with. Because every mile per hour gained since the first spark of curiosity is more than a number on a chart. It's a statement of intent. It's a declaration. It says that even in the vast indifferent silence of space, even in the face of distances that make our fastest machines seem slow, we keep trying to move forward. We keep building. We keep launching. We keep dreaming. In a way, that's what speed has always meant to humanity. Not just movement, but persistence. Not just going fast, but refusing to give up. The need to see what's next. The yearning to cross one more invisible line, to answer one more impossible question. When a rocket leaves the pad, it isn't just racing toward orbit, it's carrying thousands of years of momentum. The push of every story ever told about the stars, every thought that looked upward and wondered, every question that refused to accept we're bound to one world forever. Already moving. When you think about motion on Earth, it's easy to picture it as something relative, something small and manageable. A jog across a park, feeling your heartbeat rise, the movement of traffic through a city, rivers of red and white lights flowing along highways, the whisper of airliners drawing white lines in the upper sky, so high they're barely visible. These are the speeds that fit inside our daily experience, that make sense to our senses. We measure them in miles per hour, or kilometers if you prefer, in footsteps, in the flicker of passing scenery, in the time it takes to get from here to there. But when you step back and remember that the very ground beneath those footsteps is already moving faster than sound, faster than the fastest car ever built, everything shifts. Your perspective changes. The scale recalibrates. The planet you're sitting on is enormous, nearly 8,000 miles in diameter, massive beyond everyday comprehension. But it's not still. It's never been still. At the equator, Earth spins eastward at about 1,000 miles per hour right now. This second, every second. You don't feel it because everything around you shares that motion. The oceans rolling with the tides, the air you're breathing, the trees swaying outside, the buildings standing tall, even the chair beneath you, the bed you're lying in, the car you're sitting in, everything moves together in perfect synchrony. It's like being in a smooth train moving perfectly steadily along perfect tracks. Without the view from the window, without seeing the landscape rushing past, you'd never know you were in motion. You could pour a glass of water and it wouldn't spill. You could toss a ball straight up and it would come straight down. The motion is there, constant and powerful, but completely invisible to your senses. Yet that spin, that rotation you can't feel, gives us day and night. It's the reason the sun rises in the east every morning, the reason it sets in the west every evening. the reason time seems to flow across the sky like a river of light. But that spin is just the first layer of our planet's motion, just the beginning of the journey we're all on together. The entire Earth is also orbiting the Sun at about 67,000 miles per hour. Picture a racetrack, but the racetrack is 500 million miles around and there's nothing to race against. The sunlight that warms your face right now, that brightens your room or shines through your window, was 8 minutes old when it arrived. 8 minutes ago, it left the surface of the Sun, meaning you're already that far downstream in time before you even look up. The Sun itself is not stationary either. Nothing in the universe is truly still. It moves around the center of the Milky Way galaxy at roughly 137 miles per second, every second, carrying Earth and Mars and Jupiter and Saturn and all the rest of the solar system with it. We're all passengers on this cosmic carousel, spinning through space at speeds our ancestors couldn't have imagined. When you stack all those motions together, when you add them up like layers of a cake, you begin to realize something fascinating, something that might change how you think about your place in the universe. Even if you sit perfectly still right now, not moving a muscle, just reading or listening, just breathing, you're traveling through space at over 500,000 miles per hour. And still, you feel motionless. Still, you feel at rest. Your inner ear detects no motion. Your stomach doesn't churn. There's no sensation at all of that incredible speed. It's a strange truth about human perception, and it tells us something important about how we experience reality. We sense acceleration, not velocity. We only feel speed when it changes. The steady flow of cosmic motion passes completely unnoticed, like a current in an ocean so vast we can't see its shores. That's why when astronauts speak about being in orbit, they rarely talk about how fast they're moving. They rarely mention the 17,000 miles per hour. Instead, they talk about how beautiful it is, how still it feels, how peaceful. They describe the colors of the Earth below, the silence inside the spacecraft, the sensation of floating like they're suspended in a dream. The International Space Station moves at about 17,000 miles per hour, roughly 27 times the speed of sound. If it were a sound wave, it would break every window for miles around. Every 90 minutes, it completes a full circuit around the planet, passing from daylight to darkness and back again 16 times a day. 16 sunrises, 16 sunsets, every single day. From Earth, that orbit looks like movement. You can see the space station pass overhead sometimes, a bright dot moving steadily across the star field. From inside, it feels like suspension, as if everything has found perfect balance between the pull of gravity and the push of motion, as if all forces have cancelled out, and what's left is pure, weightless existence. The people who reach those altitudes, who live in that environment for months at a time, become the fastest humans alive in terms of pure velocity, but not in the way most of us imagine speed. Their sense of speed is visual, not physical. They see the curve of Earth rotating below, clouds curling like brushstrokes on a canvas, storms spinning silently, enormous and powerful. They watch continents drift past in minutes. Oceans fade into the curved horizon. Yet inside the capsule, inside their home in the sky, there's no sensation of rushing. Coffee floats in spherical bubbles, pens drift through the air, hair curls slowly outward in every direction. They're traveling at 5 miles per second, but it feels like calm, like meditation, like floating in warm water. The evolution of human speed. It's remarkable, almost miraculous, to think how far human speed has evolved in such a short span of history. The first humans to break what we call the sound barrier, about 767 miles per hour, did it less than a century ago. In 1947, Chuck Yeager piloted the Bell X-1 through that invisible wall and heard the sonic boom that proved it was possible. Chasing speed through history. Humanity has always chased speed. It's in our nature. From the very first runners who tested their breath against distance, who wondered how far they could go before their legs gave out, to the first sailors who learned how to harness the wind, who realized that with the right sail and the right breeze, they could move faster than any human could run, to the first pilots who broke the sound barrier, who heard that thunderous boom and knew they'd crossed into new territory. Each leap in speed has fundamentally changed how we see the world. But space travel doesn't just add more miles per hour to the tally, it changes what speed means entirely. It transforms our relationship with motion itself. It forces us to think in new ways, to measure in new units, to imagine in new dimensions. When the first rockets lifted off in the mid-20th century, they carried not just machines and fuel, but the weight of an idea, an old idea, really, an ancient dream that speed could be infinite if only we escaped Earth's pull, that the sky wasn't a ceiling but a doorway. The problem, as scientists quickly learned, is that nature charges a steep toll for leaving home. The universe doesn't give up its travelers easily. To rise above the atmosphere, you need to overcome the grip of gravity, and that means reaching what we call escape velocity. For Earth, that's about 25,000 miles per hour. Not to orbit, mind you, but to break free entirely, to sever the invisible tether that binds us to our planet. To put it another way, and let this image settle in your mind, if you could somehow hurl a stone at that speed, it would never come back down. It would slip forever into the deep. It would become a wanderer drifting through space for eternity, unless it happened to encounter another world's gravity. Every rocket you've ever seen on a launch pad is essentially a vessel designed to do exactly that, to take humans or machines and accelerate them until falling and flying become the same thing, until down and up lose their meaning. It's strange to think of fast as something that happens slowly, isn't it? But that's the nature of spaceflight. The roaring flame of a rocket, that tremendous column of fire and thunder, lasts only a few minutes. 8 minutes, 10 minutes, maybe 12, if you're going somewhere particularly ambitious. Yet what it achieves is years, sometimes decades, of drifting momentum. Once the engines shut off, once that final push is complete, the spacecraft doesn't slow down. There's nothing to slow it down. It just keeps going and going and going. In space, without air to resist it, without friction to steal its energy, motion is eternal, or as close to eternal as anything we know. Every object that's ever left Earth is still moving. The probes we sent to Jupiter and Saturn decades ago, the satellites that beam our television signals and phone calls, the discarded stages of rockets, those empty shells that did their job and fell away, all of them silent, steady, still coasting through their endless trajectories, never stopping, never slowing, unless something intervenes. This persistence is both beautiful and unsettling when you think about it. When we drive a car or fly in a plane, there's always a sense of control, of friction, of feedback from the world around us. Release the gas pedal and the car slows. Stop pedaling your bicycle, and eventually you'll coast to a stop. But in space, there's nothing to push against. Only gravity can change your path. Only the pull of distant worlds can curve your trajectory. Every maneuver requires fuel, and fuel is precious. Fuel is weight. Fuel is expensive to lift into space. So most of the time, spacecraft don't burn at all. They drift. They coast. They follow the paths that physics has laid out for them. Every kilometer per second gained during those brief moments of thrust is a gift. A little fragment of acceleration traded for years, sometimes centuries of quiet motion. When you think of speed like that, the word itself begins to blur. What does it mean to be fast in a place with no reference frame? If there's nothing standing still to measure yourself against, are you even moving? or are you simply existing in a different state? The International Space Station orbits Earth at 5 miles per second. Let that number roll around in your mind. 5 miles every single second. That's enough to circle the entire planet in about 90 minutes. To the astronauts on board, it's serene. They eat their carefully packaged meals. They sleep in sleeping bags attached to the walls. They float from module to module while continents glide past below like a slow-motion film. Meanwhile, the Parker Solar Probe, the fastest human-made object ever built, whips around the sun at over 430,000 miles per hour. That's fast enough to travel from New York to Tokyo in less than a minute. Fast enough to cross the entire United States in about 20 seconds. It's a speed so extreme it almost defies comprehension. Yet, if you were somehow riding inside it, protected from the heat and radiation, you wouldn't feel wind or vibration. You wouldn't hear the rush of motion. You'd feel nothing at all, except perhaps the gentle tug of the sun's gravity as you swung past. In space, velocity is invisible. Speed is silent. That disconnect between feeling and fact is part of what makes speed in space such an alluring, almost mystical concept. On Earth, we measure speed with experience. We feel the wind, we see the blur, we sense the acceleration in our bones. In space, we measure it with math, with numbers on screens, with calculations and predictions. And perhaps that's why the question of how fast can we travel is as philosophical as it is physical. We're really asking how far we've come in mastering movement through nothingness, how close we are to turning the dream of the stars into something tangible, how much farther we have to go before the universe feels small. If you close your eyes for a moment, you can almost imagine what that journey feels like. The sound of launch fades as you climb higher. The sky turns from blue to indigo to black. The body feels lighter, then weightless. The engines cut off and silence replaces sound. Complete, total silence. No wind, no engines, no rumble. Just the quiet hum of electronics and the sound of your own breathing. Outside, the curve of the Earth glows faintly in the sunlight. Clouds drifting across oceans like breath condensing on glass. Every direction looks the same. There is no up or down anymore, no forward or backward in any meaningful sense. Only a direction you've decided to call out, a direction you're heading because that's where you aimed your spacecraft. And in that moment, speed becomes less about going somewhere and more about being somewhere new. It's not about the velocity anymore. It's about the view, the perspective, the realization that you've left home, even if home is still visible through the window. The weight of distance. It's humbling, isn't it? To realize that our fastest machines are still crawling compared to the distances they face. Even at hundreds of thousands of miles per hour, speeds that would have seemed like pure magic to our ancestors. The nearest star would take tens of thousands of years to reach. Our technology, for all its brilliance, for all the genius and effort poured into it, has only taken baby steps across the cosmic floor. Think about that for a moment. We've built machines that can travel at nearly 500,000 miles per hour. We've bent metal and harnessed fire and calculated trajectories with incredible precision, and yet in the grand scale of things, we've barely left our front porch. The universe is just that big, that impossibly, incomprehensibly vast. And yet, each step matters. Each mission that reaches a new record, that pushes a little farther or a little faster, carries within it the momentum of all who dreamed before. Every number on a speed gauge represents countless hours of work, countless failures and redesigns, countless people who believed it was possible. Now, less than a single human lifetime later, orbital flight has multiplied that speed by 20. We've gone from breaking the sound barrier to circling the planet in the time it takes to watch a movie. It's an extraordinary leap in only a few generations, a transformation of human capability that our grandparents witnessed firsthand. Our ancestors, not so long ago, considered galloping horses the peak of motion, the fastest thing alive. 30 miles per hour felt like flying. Then came steam engines, chugging along at speeds that frightened people at first. Then propellers slicing through air, jets screaming across the sky. And finally, rockets, controlled explosions carrying people upward. Each step redefined what fast meant. Each discovery brought new limits and new ambitions. When the first astronauts climbed aboard their capsules, strapping themselves in for the unknown, they were climbing into history's most powerful accelerations. The rockets that carried them had to push through Earth's gravity with astonishing energy. More energy in a few minutes than most power plants produce in days. The Saturn V, that magnificent tower of engineering that launched the Apollo missions to the moon, was taller than a 30-story building and weighed about 3,000 tons when fully loaded. At liftoff, standing at the pad with its 5 enormous engines roaring to life, it produced 7.6 million pounds of thrust. 7.6 million. The ground shook for miles. Windows rattled. The sound was described as feeling like a physical force pressing against your chest. The first few minutes of flight were, and still are, a controlled explosion, barely controlled, some would say, hurling metal and life and hope toward the vacuum above. And then, as the engines shut down one by one, and the spacecraft reached orbit, that chaos faded into absolute quiet. The contrast is almost violent in its suddenness. The moment of transition from full acceleration to drifting weightlessness might be the most dramatic shift any human body can experience. 1 second you're pressed into your seat under several times Earth's gravity, feeling like an elephant is sitting on your chest. The next, you're weightless, floating, drifting. Everything that was heavy is suddenly light. Pens float away, arms rise on their own. The body adjusts, but the mind struggles to catch up. There's no wind in space to orient yourself, no horizon to gauge speed, no sense of up or down that makes intuitive sense. The only clue that you're moving is the view out the window, a curved planet glowing blue and white beneath a black sky. And even that view is so surreal, so unlike anything evolution prepared us for, that the brain sometimes refuses to believe it's real. And yet, for all its violence and cost, for all the fuel burned and money spent, that kind of motion has hard limits. Limits that frustrate engineers and dreamers alike. The tyranny of the rocket equation. Rockets are fundamentally constrained by the fuel they must carry. It's an inescapable truth. Every kilogram of propellant adds weight to the vehicle, and the heavier a rocket becomes, the harder it is to accelerate. You need more fuel to lift that fuel, which makes you heavier, which means you need even more fuel. This vicious cycle is known as the tyranny of the rocket equation, a simple but merciless truth discovered by early engineers like Tsiolkovsky and Goddard. To go faster, you must carry more fuel. But carrying more fuel makes you heavier, which means you need even more fuel to push that added weight. And the cycle continues in an exponential spiral. Eventually, you reach a point where adding more fuel doesn't help anymore, where the weight of the fuel itself cancels out any benefit it might provide, where the numbers simply stop working no matter how hard you try. That's why rockets are staged, built in layers like a matryoshka doll that detach as they burn. The first stage, the biggest and most powerful, gets the vehicle moving and lifts it through the thickest part of the atmosphere. Then, when its fuel is exhausted, it falls away, drops back to Earth or into the ocean. Only by constantly shedding weight can a rocket climb towards space and towards speed. It's easy to imagine that once you reach space, once you're beyond the atmosphere, you can simply accelerate forever, point your engines in one direction and keep burning until you reach whatever speed you want. In theory, that's absolutely true. Without air resistance, Without friction, there's nothing to slow you down. You could accelerate indefinitely if you had infinite fuel. But in practice, it's rarely that simple. You still need to burn propellant to keep accelerating. Chemical rockets work by throwing mass out the back very fast, and eventually, inevitably, propellant runs out. The tank empties. The engines go silent. Most spacecraft spend only a short burst of time accelerating, minutes or maybe hours, then coast the rest of the way to their destinations. It's a careful dance between energy and patience, between thrust and conservation, between ambition and physics. The fastest humans so far, the human beings who have traveled at the highest velocity ever recorded, weren't on orbiting stations floating peacefully. They were the Apollo astronauts returning from the moon. As their capsules fell back toward Earth after their lunar journey, gravity became their engine. They reached speeds of nearly 25,000 miles per hour before slamming into the atmosphere. At that speed, the air in front of their heat shields compressed and glowed like molten metal. The friction was so intense, so extreme, that the temperature outside exceeded that of the surface of the sun itself. Thousands of degrees, hot enough to vaporize almost any material instantly. And yet, protected by their heat shields and their precisely calculated trajectory, the crew inside felt only vibration and the steady pull of re-entry. They could hear the roar through the hull. They could feel the deceleration pressing them into their seats. But they survived. They made it home. That number, about 7 miles per second, remains the record for crewed human travel. It's a small fraction of the speeds we imagine in science fiction, where ships jump to hyperspace or travel at warp speed. But it's a monumental achievement for a species that only learned to fly little more than a century ago. Every meter per second gained has been earned with ingenuity, risk, and fire. When you compare that to the machines we've sent farther out, the uncrewed probes and rovers and orbiters, it puts our place in perspective. The Voyager probes, those twin explorers launched in the 1970s with messages for any alien civilization that might find them, are now beyond the edge of our solar system. Each is traveling at about 10 miles per second, faster than any crewed spacecraft ever has. Faster than seems possible for something so small and old, but still far, very far, from light speed, still crawling by the standards of the universe. In the grand scale of the cosmos, these speeds are glacial. Light travels at 186,000 miles per second, not per hour, per second. It's a speed so fast that light from the sun takes only 8 minutes to reach Earth across 93 million miles of empty space. Even the Parker Solar Probe, our current record holder for velocity, reaches only about 0.06% of that. For humans, that's breathtaking. For the cosmos, it's barely motion. It's like watching a snail cross a football field and calling it fast. Still, the importance of that scale, of those tiny percentages and enormous numbers, can't be overstated. Space is vast, not just in distance, but in emptiness, in the sheer nothingness between points of light. When you look up at the night sky, especially on a clear night far from city lights, the stars seem close enough to trace with your finger. They feel intimate somehow, present. In truth, even the nearest one beyond our sun, Proxima Centauri, is over 4 light-years away. 4 years traveling at the speed of light. At the speed of the fastest human-made probe, it would take more than 70,000 years to arrive. That's longer than all of recorded human history, longer than civilization itself, longer than we've had writing or agriculture or cities. You could launch a probe today, and your descendants 70,000 years from now, people as different from you as you are from the first humans to leave Africa, might see it arrive. Speed, it turns out, is profoundly relative to the size of your world. When you travel across a city at 60 miles per hour, it feels fast because the buildings rush by. When you travel across the solar system at tens of thousands of miles per hour, there's nothing to compare against. Nothing rushes by, nothing changes for months or years at a time. Motion stretches out into stillness. The mind loses its sense of scale, its sense of progress. You're moving incredibly fast and going nowhere all at once. That's why astronauts describe space as both infinite and intimate. Infinite in its size, in its distances, in the number of stars and galaxies and cosmic mysteries. Intimate in its silence, in the way you're separated from the void by only a thin shell of metal and plastic, in how personal and immediate it feels despite the scale. Time itself bends. There's another layer to this story, another dimension to consider. Moving fast doesn't just change your location in space, it changes time itself. It bends the fabric of reality in ways that seem impossible but are absolutely measurably real. According to Einstein's theory of relativity, time slows down for objects in motion relative to those at rest. The faster you go, the slower your time passes compared to the world you left behind. It's one of the strangest predictions of modern physics, and also one of the most thoroughly tested and confirmed. It's not just theory, it's not just equations on a blackboard, it's been measured precisely, repeatedly. The difference is tiny at ordinary speeds, almost impossible to detect, but measurable for astronauts and satellites moving at orbital velocities. On the International Space Station, time moves a few microseconds slower per day compared to clocks on Earth. Microseconds, millionths of a second, almost nothing, but measurable, real. That means astronauts who spend months in orbit come home ever so slightly younger than if they'd stayed on the ground. It's a subtle effect, so small you'd never notice it without atomic clocks. But it reminds us that speed isn't just about space. It bends time too. The faster we move, the more reality itself adjusts to accommodate that motion. The universe reshapes around us. When you think about it, really sit with that idea. That's astonishing. Simply traveling fast enough changes the rhythm of your existence, changes how quickly you age, changes when in time you arrive at your destination. Even if only by a fraction of a second, even if only by an amount so small it barely matters, the effect is there, real, measurable. Perhaps that's why space exploration feels as philosophical as it is technological, why it captures imaginations in ways other engineering projects. We're not just measuring how far or how fast we can go, we're testing the boundaries of what motion even means, what reality means, what time and space and existence mean when you push them to their limits. Each new velocity we achieve touches the edge of physics and human endurance alike. Each record broken is a small step toward understanding the universe's deepest rules. For the astronauts who ride those speeds, who live at those velocities for months at a time, there's a paradox they all eventually recognize. To go faster, you must surrender control. You can't steer like a car. You can't adjust your speed on a whim. Every launch is a commitment to let go, to trust the equations that were calculated months or years before, the machinery that was built by thousands of hands, and the invisible laws of physics that carry you forward. On Earth, speed often means freedom. You press a pedal and accelerate, turn a wheel and change direction. Feel the wind rushing past. You're in control, or at least it feels that way. In space, speed means surrender. There's no friction to fight against or use for steering, no air to push on, no stopping once the fuel is gone. You're a projectile, a bullet fired from a gun, coasting on pure momentum until something else changes your path. It's humbling, perhaps a little frightening when you first grasp it, yet it's also beautiful in its own way, because every mission, every orbit, every trajectory is an act of faith in motion itself. Faith that the universe is consistent enough, predictable enough for us to navigate through it, that the laws of physics won't change. that our calculations were correct. The fastest humans alive may not feel the wind or the rush like a motorcycle rider or a skydiver, but they live at the threshold of what's possible for our species right now, in this moment of history. They embody a kind of quiet velocity, not the roar of speed, but the silence of mastery, not the chaos of acceleration, but the calm of momentum. Their motion is smooth, steady, patient, measured against the backdrop of infinity, and in that smoothness lies achievement. And so it's worth remembering, worth really taking to heart, that the story of how fast we can travel isn't only about records or engines or fuel efficiency. It's about perspective, about how we see ourselves in relation to the cosmos. Against the immensity of the cosmos, our speeds are almost stillness. We're barely moving at all by the universe's standards, but within the fragile limits of biology and engineering, within the constraints of human ingenuity and courage, they are miracles. Small miracles, perhaps, quiet miracles, but miracles nonetheless. Every kilometre per second we achieve is a whisper of progress, a small proof that we're learning to move, not just through space, but through understanding, through the barriers of ignorance and fear, through the limits we once thought were absolute. The earth keeps turning beneath us. The sun keeps pulling us forward. The galaxy keeps sweeping us through its spiral arms in a dance that began billions of years before we existed. Even in stillness, we are voyagers. Even in rest, we are travelers moving at incredible speeds. Even in sleep, we are fast. Escaping the cradle. The farther you go from Earth, the more you begin to understand that everything about speed, every discussion of velocity and motion, is tied to one simple, profound act: escape. It's a word that feels emotional, almost human. We escape from danger, from boredom, from places that hold us back. But in physics, in the mathematics of spaceflight, it means something precise and beautiful. To escape is to reach a velocity where gravity's pull can no longer call you back, where the invisible tether that binds you to your homeworld finally breaks. For planets, for moons, for any massive object, that pull defines the boundary between what belongs and what drifts away forever. For Earth, our blue marble home, the escape velocity is about 7 miles per second. In the more familiar terms we use every day, that's roughly 25,000 miles per hour. If you could somehow throw a ball that fast, launch it perfectly straight up, it would never come back down. It would climb and climb, fighting against gravity the whole way, until the air was gone, until the blue sky faded into black, and it would keep going without ever falling home again. Every spacecraft we've ever launched has had to face that number, a kind of cosmic speed limit, written not by law or regulation, but by gravity itself, by the mass of the planet and the fundamental forces of nature. Gravity is both our protector and our warden, and that's a tension we've lived with since the beginning. It holds our atmosphere close, keeping the air we breathe from drifting away into space, keeps our oceans in place, preventing them from floating off as giant spheres of water, and ensures that the moon never drifts away, that it stays in orbit generation after generation. But gravity also makes escape expensive, incredibly, almost prohibitively expensive. Every gram lifted from Earth must fight against the pull of a planet that weighs 6 trillion tons. That's a 6, followed by 21 zeros. The number is almost too big to comprehend. The energy needed to overcome that pull is enormous, staggering, almost unreasonable. And most of what we call rocket science, all those complex equations and engineering challenges, is really about finding ways to balance that equation, to make the impossible merely difficult, to turn dreams into trajectories. It's strange how much energy it takes just to stop falling, isn't it? Because that's what spaceflight really is. When you strip away the romance and look at the physics, when you orbit Earth, you're not floating above gravity like some people imagine. You're not beyond its reach. You're falling toward Earth constantly, but because you move forward so fast, at about 5 miles per second, the planet's surface keeps curving away beneath you at the same rate you fall. The International Space Station, that brilliant laboratory circling overhead, is constantly falling toward Earth every second of every day, but because it moves forward at about 5 miles per second, the planet's surface drops away just as quickly as the station falls toward it. The result is continuous free fall, a perfect, beautiful balance between descent and motion. That precarious balance is what we call orbit. To go faster than orbit, to truly escape and not just circle, you have to push even harder. You have to add more speed, more momentum, more energy. Rockets do this by burning fuel in stages, shedding weight as they climb. The first stage, the massive booster at the bottom, gets the vehicle moving, lifting it through the thickest part of the atmosphere, where the air fights back with every meter of altitude. Then, when its fuel is exhausted, it falls away to shed weight, returns to Earth, or splashes into the ocean. The next stage takes over immediately, adding more speed with every second of combustion, building on the velocity already achieved. And sometimes there's a third stage, smaller still, that gives the final push. By the time the upper stage finishes its work, the spacecraft is beyond air, beyond friction, beyond the thickest parts of Earth's gravitational well, and gliding at tens of thousands of miles per hour. Only then, after all that effort and fuel and fire, can gravity begin to loosen its hold. Only then does escape become possible. The beauty of this process, the thing that makes it almost poetic, is how much of it depends on patience and precision rather than raw power. A rocket may look like raw power when it launches, all those flames, that thunder that shakes the ground for miles, the acceleration that pins astronauts to their seats. But underneath the spectacle is choreography, dance, mathematics. Engineers calculate every angle with incredible precision, every second of thrust, every gram of propellant, every moment of the flight path. A tiny error in velocity, just a few meters per second off target, can mean the difference between orbit and failure, between success and burning up in the atmosphere. There's a kind of poetry in that balance, in that precision. You're building a machine whose entire purpose is to fall upward, to use controlled explosions to defeat gravity, to transform chemical energy into altitude and speed. When you watch footage of a rocket launch, whether it's an old Saturn V or a modern Falcon or a Soyuz, it's easy to focus on the spectacle, the sound that rattles your chest, the fire brighter than anything except the sun, the columns of vapor trailing into the sky like white roads to heaven. But what's really happening underneath all that drama is a carefully managed exchange of energy. The chemical bonds inside the fuel, bonds that hold molecules together, are being torn apart to release motion. Inside the engines, temperatures rise to thousands of degrees, hot enough to melt steel instantly, and combustion gases, the products of that violent reaction, are expelled downward at supersonic speeds, faster than sound, faster than most jets can fly. Every molecule of exhaust is a push against gravity. Every moment of burn adds another few hundred meters per second to your velocity. It's Newton's third law in its purest form. For every action, an equal and opposite reaction. Push the gases down, and the rocket goes up. For the people inside, strapped into their seats and waiting, that push feels like pressure, weight. During launch, astronauts experience acceleration forces of 3 to 4 times Earth's gravity. Breathing becomes heavier, like someone is sitting on your chest. Muscles tighten involuntarily. The body senses motion not as speed or distance, but as weight pressing down from above. Then, after long minutes of that relentless climb, after riding that column of fire toward the edge of space, the engines cut off. The silence is sudden, shocking, The weight disappears instantly. Everything floats. Pens drift out of pockets. Arms rise on their own if you don't hold them down. Hair spreads out in every direction. And for the first time, if it's your first flight, Earth looks like what it really is. A sphere, not flat like it seems when you're standing on it. Not endless, but curved, finite, beautiful. The horizon bends gently, a perfect arc. The atmosphere becomes a faint blue haze, thin as tissue paper. There's no up or down anymore, no north or south in any meaningful sense. Only direction, only forward, backward, toward, away. That moment, the instant when gravity loosens its grip and you transition from having weight to being weightless, is one of the most transformative experiences a person can have. Many astronauts describe it with words like awe, or wonder, or overwhelming. Not just at the view, though the view is spectacular, but at the realization of distance, of what you've just accomplished. You've left the cradle, as the Russian scientist Konstantin Tsiolkovsky once wrote, but you haven't yet learned to walk among the stars. You're suspended between home and infinity, between everything familiar and everything unknown. Tsiolkovsky was one of the first people to put serious numbers to the dream of escape. Living in the late 19th century, long before rockets existed as anything more than fireworks, he worked out the mathematics of reaching orbit and beyond. He showed that to achieve escape velocity, a spacecraft would need to carry an enormous amount of fuel and expel it at very high speed. His equation, still used today by every space agency, revealed the cruel truth of rocketry, that small increases in speed require exponentially more fuel, that the faster you want to go, the harder it gets. That insight was both sobering and inspiring. It meant space travel was possible in theory, that the laws of physics allowed it, but it also meant it would never be easy, never be cheap, never be simple. His ideas spread quietly at first through scientific journals and engineering circles in Russia and beyond, but they became the foundation for everything that followed. When Robert Goddard launched the first liquid-fueled rocket in 1926 in a snow-covered field in Massachusetts, it was the physical embodiment of Tsiolkovsky's dream. When von Braun built the V2 and later the Saturn V, he was following equations Tsiolkovsky had written decades earlier. The scientist himself never lived to see humans reach space. He died in 1935, decades before Sputnik. But his phrase, "Earth is the cradle of humanity, but one cannot remain in the cradle forever," became a kind of mantra for explorers, a rallying cry, a reminder of why we push toward the stars. To escape the cradle is to grow up as a species, to accept the risks and rewards of motion beyond home, to acknowledge that staying in one place, no matter how comfortable, is not our destiny. The first real escapes from Earth's gravity were uncrewed, small metal capsules, barely bigger than trash cans, hurled into the void on columns of flame. They didn't last long. Most burned up or crashed, but they proved the principle. They showed that escape was possible, that Tsiolkovsky's equations worked in practice, not just on paper. Then came Sputnik on October 4th, 1957, the first artificial satellite launched by the Soviet Union from a secret facility in Kazakhstan. It orbited Earth once every 96 minutes, broadcasting a simple beeping signal that could be heard around the world on shortwave radios. For the first time in billions of years, humanity had placed something beyond gravity's permanent reach. That sound, faint and mechanical, and strangely lonely, was the heartbeat of escape, the sound of the future arriving. Only 4 years later, on April 12, 1961, Yuri Gagarin became the first person to orbit Earth. His capsule Vostok 1 reached a maximum speed of about 17,000 miles per hour. It was barely enough to maintain orbit, just above the minimum needed. but it was enough to make history, enough to change everything. When he returned, parachuting down into a farmer's field, he described the sight of Earth from space with simple words. "The Earth is blue. How beautiful it is." In that moment, he wasn't just a pilot following orders. He was the first human to experience what it means to leave the planet's pull entirely, to see home from the outside, to escape, even if just for 108 minutes. Escaping gravity is an achievement of physics, of engineering, of mathematics, but staying out there, maintaining orbit, or traveling farther is an achievement of balance. Once you're in orbit, every movement matters, every action has consequences. Fire the engines too long in one direction and you drift higher. Your orbit gets bigger, slower, farther from Earth's curve. Fire them too briefly and you descend back into the atmosphere where friction will grab you and pull you down. The precision required is extraordinary, measured in fractions of a second, in meters per second of velocity change, and yet the outcome, when you get it right, is effortless grace. A spacecraft can circle the planet indefinitely, generation after generation if maintained, neither falling nor flying away, just gliding through the balance point between competing forces. When the Apollo missions set their sights on the moon in the 1960s, they had to take that precision even further. To travel from Earth to another world, you don't just aim at where the moon is and thrust. You aim at where it will be 3 days from now when you arrive. You time your motion so that your curved path through space intersects with a moving target hundreds of thousands of miles away. It's like throwing a baseball at a target on a speeding train while you're on a different speeding train, except both trains are invisible and the distances are vast. The spacecraft accelerates until Earth's gravity releases its dominant hold. Then it drifts along a carefully calculated trajectory that eventually falls into the moon's weaker gravitational pull. It's a controlled fall from one cradle into another, from one sphere of influence to the next. At the midpoint of that journey, astronauts are in what's called translunar coast, a vast, empty stretch of space where Earth is no longer dominant, and the moon is not yet strong enough to capture them, where they're truly between worlds. In that space, motion feels pure, crystalline, no engine noise except when they make small corrections, no resistance, only the quiet arithmetic of velocity and distance playing out exactly as Newton's laws predict. The Apollo crews traveled that path at speeds of about 7 miles per second after their initial boost, coasting on the momentum gained from their translunar injection burn. They had escaped Earth completely, something only 24 humans have ever done. There's a subtle irony in how all this works, a counterintuitive truth that surprises people. To leave Earth, you don't actually have to reach escape velocity all at once. You don't need that full 25,000 miles per hour immediately. If you can apply steady thrust over time, even gentle thrust, a spacecraft can spiral outward gradually, gaining speed bit by bit until it drifts free, like climbing a spiral staircase instead of jumping straight up. That's how many interplanetary missions operate these days. Slow, deliberate, energy efficient, patient. The Parker Solar Probe, for instance, didn't need to accelerate to its incredible record-breaking speeds at launch. Instead, it used repeated gravity assists from Venus to adjust its path and increase its speed relative to the Sun. Each flyby added more velocity, bent its trajectory a little more, sent it a little closer to our star. Over years, those small nudges accumulated into the fastest human-made object ever built. In space, patience is often the most effective engine. Time is fuel, waiting is strategy. Still, the concept of escape velocity carries a kind of poetic weight that persists despite these workarounds. It represents freedom, but also responsibility. To escape means to leave behind the safety of air that protects us from radiation and meteorites. the warmth of atmospheric pressure that our bodies evolved to need, the comfort of certainty, of knowing exactly where you are and what will happen next. It's a commitment to inertia in its purest form. Once you cross that line, once you exceed escape velocity, there's no friction to stop you. You will keep moving in that direction until something intervenes. Another planet's gravity bending your path, a carefully timed maneuvering burn, or simply the slow decay of your orbit if you're still close enough to Earth that faintest wisps of atmosphere can gradually slow you down over years or decades. And this is where human imagination begins to collide hard with physical reality. Our rockets can push us to incredible speeds that would have seemed like magic a century ago, but every step faster, every additional mile per hour requires exponentially more energy. The curve is brutal, unforgiving. The power to reach low Earth orbit already consumes hundreds of tons of fuel. To double that speed, to go from orbital velocity to escape velocity, you'd need more energy than most small nations produce in a day. And to go faster still, to reach the kinds of speeds needed for rapid interplanetary travel, the energy requirements become almost absurd. That's why so much of modern propulsion research focuses not on brute force, not on bigger rockets and more fuel, but on efficiency, on finding clever ways to make escape less costly, to stretch each drop of propellant a little farther, to use the environment itself, gravity and solar radiation, to help propel spacecraft. Nothing drives that accelerate particles to incredible speeds but use very little fuel. Solar sails that catch the pressure of sunlight like ships catching wind. Nuclear propulsion that could provide steady thrust for months or years. All of these ideas emerge from the same fundamental challenge. How do you keep accelerating once you've already escaped Earth's immediate pull? How do you keep building speed in an environment with nothing to push against? Because once you're free from gravity's strongest grip, once you're in deep space between worlds, speed becomes a matter of persistence rather than explosive force. The fastest spacecraft we've built achieved their records not through violent burns lasting minutes, but through continuous gentle acceleration over months or even years. Patience compound ed over time becomes exponential growth. That's a different kind of escape, one that values endurance over violence, consistency over explosiveness. But before any of that can happen, before we can dream of deep space missions and interstellar travel, we still have to climb out of our planet's gravitational well, and every launch, every single time a rocket lifts off, reminds us just how deep that well is, how much effort it takes just to reach the first step. Even the smallest orbital rocket must fight through an atmosphere that pushes back with every meter of altitude gained. The sound of that fight, the heat of friction as metal pushes through air, the vibration that rattles every bolt and weld. It's all part of breaking bonds, of severing the ties that hold us to our birthplace. You can almost think of it as birth on a planetary scale. The roar of engines like the first cry, the vibration and chaos like the struggle of transition. And then the roar fades, the cradle opens, and something new, something that was earthbound moments before, drifts free into the dark. Escaping Earth isn't just a technical feat, though the technical challenges are enormous. It's a psychological one as well. We evolved to belong here, to breathe this specific mixture of gases, to walk under this specific pull of gravity, to feel the comfort of weight pressing us down, anchoring us, keeping us connected. The moment that pull disappears, the moment weightlessness arrives, the brain needs to adapt to something it was never designed for. Astronauts described floating not as freedom at first, but as disorientation, confusion. The inner ear, which uses gravity to tell you which way is up, loses its bearings completely. The body can't tell up from down anymore. The heart shifts position slightly in the chest, moving upward. Blood redistributes, flowing into the upper body and head, making faces puffy. Even sleep feels strange, deeply strange, when your body no longer presses against a bed, when there's no sensation of lying down because down has ceased to exist, when you close your eyes but your body still feels like it's falling even though you're completely still. Escape requires adjustment, physical, mental, emotional. And yet, once that adjustment comes, once the brain rewires itself to understand this new reality, the feeling changes completely. The mind expands instead of contracting. What felt disorienting becomes liberating. What felt wrong becomes natural. The view out the window no longer looks like a distant horizon you're observing. It looks like a connection, a relationship. Every orbit becomes a meditation on scale, on perspective, on what it means to be human in an infinite cosmos. Cities blur into clusters of light at night, golden and white against the darkness. Storms swirl like living things, massive and powerful and beautiful. The line between sky and space, that gradient from blue to black, vanishes when you're on the other side of it. You realize something profound in those moments, that escape didn't mean leaving home. It meant seeing home clearly for the first time, seeing it whole, seeing it as it truly is. A single, fragile, beautiful world suspended in an ocean of nothing. To escape the cradle is not to abandon it, not to reject it or leave it behind forever. It's to understand that the cradle was always moving, that Earth itself is part of a larger motion, a grander dance, that we're all already traveling through space at incredible speeds whether we launch rockets or not, and that stepping away from it, even briefly, allows us to see that motion for what it is, allows us to see ourselves for what we are. Every spacecraft that leaves Earth carries a small piece of that realization with it, even the ones that never return. The Voyagers sailing beyond our solar system, the pioneers that came before them, the New Horizons probe that visited Pluto and is now heading farther still. Each one is a message cast outward into the cosmic ocean, a quiet declaration that we learned how to let go, that we found the courage to fall upward. And perhaps that's the heart of it, the deepest truth beneath all the mathematics and engineering. Escaping the cradle isn't about defiance or rebellion, it's about trust. Trust in physics, in the laws that govern motion and energy, trust in engineering, in the machines we build with such precision, trust in human curiosity, in that deep hunger to know what lies beyond the next horizon, and trust in the vast silence that waits beyond our atmosphere, the silence that terrifies and beckons in equal measure. Because every escape is also an arrival. Beyond gravity lies freefall. Beyond air lies vacuum. Beyond everything familiar lies something we're still learning to name, but it's there, waiting, and we keep reaching for it, one launch at a time, one orbit at a time, one mission at a time. The speed we've achieved so far, the velocities we've reached are just the beginning, the first words in a very long conversation with the cosmos. And every kilometer per second we add to that speed, every new record we set, brings us one small step closer to becoming a truly spacefaring civilization. The dream of going faster. So where does this leave us? Here, now, in this present moment with all our technology and understanding, how fast can we actually travel? The answer depends on how you measure it, on what counts as we. If we means humans, flesh and blood astronauts strapped into seats and breathing recycled air, then the record still stands at about 7 miles per second, 25,000 miles per hour. The Apollo astronauts returning from the moon achieved that, and no human has gone faster since. That was more than 50 years ago now, half a century, and yet the record remains. It's a reminder of how difficult it is to push biological beings to higher speeds. The human body is fragile. It needs air and water and food. It needs protection from radiation. It can only withstand so much acceleration before blood vessels burst and organs fail. Every additional mile per hour carries risks that multiply as speed increases. If we means machines, uncrewed probes and spacecraft that don't need life support or return tickets, then the record belongs to the Parker Solar Probe, 430,000 miles per hour, fast enough that if you could somehow see it pass by, it would be just a blur, a streak, gone before your eye could focus. That speed was achieved not through massive engines or enormous fuel tanks, but through patience and cleverness, by using Venus's gravity repeatedly to bend its path and add velocity, by falling toward the sun and using that fall to accelerate, by working with the environment instead of fighting against it. And yet, even that incredible achievement, that record-breaking velocity that makes everything else we've built seem slow, is still just a fraction of what the universe offers. Light, electromagnetic radiation traveling through the vacuum, moves at 186,000 miles per second. The Parker Solar Probe, for all its speed, reaches only about 1/20th of 1% of light speed. It would take more than 6,000 years to reach the nearest star at that velocity. The universe is teaching us a hard lesson, that space is not just big, it's incomprehensibly vast, and that our current speeds, impressive as they are by human standards, are barely enough to explore our immediate neighborhood. But here's the thing. Here's what keeps engineers and dreamers awake at night, sketching designs and running calculations. We're not done, not even close. The speeds we've achieved so far represent only the beginning of what's possible with chemical rockets. With the technology we understand right now, today, there are other possibilities, other paths forward. Ion drives that can run for years, slowly building speed until spacecraft reach velocities chemical rockets never could. Nuclear thermal rockets that heat propellant to incredible temperatures, providing much more thrust per kilogram of fuel. Solar sails that catch starlight itself, using photons as wind. Fusion rockets, if we can ever make fusion work reliably. Each of these technologies could multiply our speed many times over. And beyond those relatively near-term possibilities lie ideas that sound like science fiction but are rooted in real physics. Generation ships that would carry humans for centuries between stars, their ecosystems closed and self-sustaining. Laser propulsion that would use enormous ground-based lasers to push lightweight sails to significant fractions of light speed. Even concepts like antimatter rockets, though the engineering challenges there are staggering. Some scientists have even explored concepts like warp drives and wormholes, ways to cheat the speed limit by bending space itself rather than moving through it. Whether such things are truly possible, whether the universe allows such shortcuts remains unknown. The mathematics suggests maybe. Experiments remain impossible with current technology, but the fact that we can even discuss such ideas seriously shows how far our understanding has come. For now, though, we work with what we have: chemical rockets and gravity assists, careful planning and patient coasting, small incremental improvements that add up over decades. It's not glamorous. It doesn't match the instant jumps to hyperspace we see in movies. But it's real, it's working, and it's taking us places our grandparents could only dream about. Mars rovers exploring ancient riverbeds, probes diving through the geysers of Enceladus, spacecraft visiting Pluto and the Kuiper Belt. Each of these missions pushed the boundaries of speed and distance a little farther. Each one taught us something new about how to move through space efficiently. And each success builds the foundation for the next leap. The next record, the next impossible thing that becomes routine. The question of how fast we can travel is really a question about time, not just the time it takes to reach destinations, but the time it takes for technology to mature, for ideas to become reality, for dreams to become engineering specifications. Every generation looks at the speeds available to them and thinks they're pushing the limits, and they are, until the next generation comes along and pushes farther. That's the pattern. That's how progress works. Not in sudden leaps usually, but in steady accumulated effort. Thousands of small improvements that eventually cross a threshold and become revolutionary. The Apollo program seemed revolutionary because it was, but it built on decades of rocket development, on World War II missile technology, on the insights of Tsiolkovsky and Goddard and Oberth, on countless engineers solving countless problems. The moon landing was one giant leap for mankind because it stood on millions of tiny steps taken by people whose names we'll never know. The same will be true of whatever comes next. When humans finally reach Mars, when we establish permanent bases beyond Earth, when we send probes to the nearest stars, it will seem sudden, revolutionary, but it will rest on decades of work happening right now, in laboratories and mission control rooms, in university research departments, and private company workshops. Thousands of people adding their small contributions to the great project of moving faster. So how fast can we travel in space right now? The honest answer is fast enough to explore our solar system, fast enough to send probes to every planet, fast enough to study comets and asteroids up close, fast enough to begin understanding the space environment that surrounds us. But not fast enough yet to make interstellar travel practical. Not fast enough to reach other stars in a human lifetime. Not fast enough to truly call ourselves a spacefaring species in the grandest sense. We're in an intermediate stage, no longer bound completely to Earth, but not yet free to roam the galaxy. We've escaped the cradle, but we're still learning to walk, still building our strength, still figuring out which direction to head first. And maybe that's okay. Maybe this is exactly where we should be at this point in our development. Learning patience, learning to work with the constraints the universe imposes, learning that speed alone isn't the only measure of progress. After all, the fastest journey is meaningless if you don't survive it, if you don't learn from it, if you don't return to share what you discovered. The astronauts who traveled at 7 miles per second to the moon brought back more than rocks. They brought back perspective. Photographs of Earth rising over the lunar horizon, stories of what it felt like to stand on another world. The knowledge that it's possible, that we can reach beyond our cradle when we commit to trying. That might be the most important speed of all. Not how fast we move through space, but how fast we move through understanding. How quickly we transform from dreamers to explorers, from children of Earth to children of the cosmos. A quiet closing, and so we arrive back where we started, here in this quiet moment, you and I, you, wherever you are, listening to these words. Me, sharing thoughts about speed and space, and the strange relationship between motion and stillness. We've covered a lot of ground tonight, or rather, a lot of space. We've talked about spinning planets and orbiting spacecraft, about escape velocity and the tyranny of the rocket equation, about astronauts who've traveled faster than anyone else and probes that now sail beyond our solar system, about the dream of going faster still. But beneath all those facts and figures, beneath the speeds and distances and records, there's something simpler, something human. A story about reaching, about the gap between where we are and where we want to be, about learning to cross that gap one small step at a time. Right now, this moment, you're still traveling at incredible speeds. The Earth is still spinning beneath you, still orbiting the sun. The solar system is still moving through the galaxy. None of that has stopped while we've been talking. You're still one of the fastest travelers in the universe, just by existing, just by being here. And maybe that's the perfect thought to drift off with. That motion is our natural state. That we're not meant to stay still. That even in sleep, even in the deepest rest, we're voyagers, part of something vast and ancient, and constantly moving forward. Thank you for taking this journey with me tonight, for letting these thoughts wash over you at their own gentle pace. If you enjoyed our time together, if these ideas helped you relax or wonder, or simply slow down, please consider subscribing to The Sleepy Professor. There are more journeys to take, more questions to explore softly, more science to discover at a pace that lets your mind wander. Leave a like if this resonated with you. Share your thoughts in the comments. Tell me what you think about when you look at the stars. What questions keep you curious? What mysteries call to you from the darkness between worlds? And know that whether you're drifting towards sleep or simply taking a moment to breathe, you're exactly where you need to be, moving at exactly the right speed, part of the grand cosmic dance that began billions of years ago and will continue long after we're gone. The question of what's next. The price of acceleration. Every journey through space begins with fire, not metaphorical fire, but the literal kind. The roar of chemical combustion, powerful enough to lift steel and human lives against the pull of an entire planet. Rockets are, in their simplest form, machines built to throw mass in one direction so they can move in the other. It's a simple principle with impossible demands. Every meter per second gained comes with a cost, a price measured in energy, fuel, and precision. The price of acceleration is written in the language of physics, and there's no negotiation. When a rocket stands on the launch pad, it's a tower of stored potential. Inside its tanks are propellants, usually a fuel and an oxidizer, waiting to meet in the combustion chamber. On Earth, engines can draw oxygen directly from the atmosphere, but space offers nothing to burn with, so rockets carry their own oxidizer, which means more mass, which means more fuel to push that mass, and so on. The result is a delicate, towering compromise. The structure itself is mostly fuel. Less than 10% of its weight at launch is payload. The capsule, instruments, or satellites it's meant to carry. Everything else exists only to disappear. As the engines ignite, thousands of kilograms of propellant are consumed every second. The pressure builds. The sound becomes a physical force, and the air ripples under the blast. Slowly, impossibly, the rocket begins to rise. For a few seconds it looks hesitant, almost clumsy, as if reconsidering its decision to leave. Then, as the thrust overcomes gravity, it climbs, accelerating faster and faster as the fuel burns away and the weight drops. Every second of combustion increases speed, but also consumes the very resource that makes acceleration possible. That's the first lesson of rocketry. Motion is always borrowed, never free. To understand the scale of this exchange, consider what it takes to reach orbit. The Saturn V, the rocket that carried Apollo missions to the moon, burned through about 20 tons of fuel every second in its first stage. In the 2.5 minutes before separation, it consumed over 2,000 tons of propellant, the equivalent of an Olympic swimming pool of fire disappearing in less time than a song. The energy released by that burn could power a city for hours, but in spaceflight, it barely covers the first few hundred kilometers of climb. The air thins quickly as the rocket ascends. At around 50 kilometers above sea level, the blue fades toward darkness. The engines burn more efficiently there because there's less drag, but control becomes more delicate. A small deviation in thrust can send the entire vehicle off course. Guidance systems, gyroscopes, and computers work continuously to keep it steady. Pilots or automated programs adjust the vector of the engines by degrees, so the rocket follows the proper arc, steep enough to escape gravity, shallow enough to establish orbit. Every second, the path changes, and with it, the balance between upward and forward velocity. When the first stage finishes its burn, it detaches and falls away, tumbling back through the atmosphere to be destroyed or recovered. The second stage ignites, adding more speed. Each stage is lighter, faster, and shorter-lived than the one before. By the time the final engine cuts off, the spacecraft has reached its target velocity, about 5 miles per second if it's entering low Earth orbit, or 7 if it's leaving entirely. Beyond that, there is no more upward motion, only motion along the curve of the planet. The engines shut down, the noise stops, and the violent acceleration turns instantly into stillness. Inside, astronauts describe that moment as eerie. The pressure that had pinned them to their seats vanishes. Objects drift. The only sound is the quiet hum of life support systems. After minutes of crushing force, there's sudden freedom. The body and mind adjusting to a state where there's no top or bottom, no sense of speed, just the soft inertia of success. Outside the window, the Earth glows below, enormous and silent. That transition marks the boundary between energy and emptiness. The engines can rest, but the cost of getting there is immense. For every kilogram delivered to orbit, dozens were burned in the process. The economics of acceleration are unforgiving. That's why space agencies spend so much effort refining every gram. Lighter materials, more efficient engines, smarter trajectories. Every kilogram saved on structure is a kilogram gained for science or crew or future thrust. The earliest rockets were crude but powerful. They used simple chemical reactions, liquid oxygen combined with kerosene or liquid hydrogen to create thrust. The physics are elegant. Combustion heats gas. The gas expands, and when forced through a nozzle, it accelerates outward. The reaction pushes the rocket forward with equal force. This is Newton's third law in its purest form. For every action, an equal and opposite reaction. But nature doesn't give anything for free. The faster you want to go, the more mass you must expel, and the faster you must expel it. This is where the rocket equation appears again, a compact formula that determines the relationship between velocity, exhaust speed, and the ratio of starting mass to final mass. Written simply, it says that velocity equals exhaust speed multiplied by the natural logarithm of that mass ratio. What it really means is that each extra increment of speed demands exponentially more fuel. To double your velocity, you need far more than double the propellant. That's why rockets look so disproportionate. Thin needles of payload sitting on mountains of fuel. The price of acceleration isn't only in fuel, though it's also in stress. The faster a rocket climbs, the greater the aerodynamic forces. As it passes through the lower atmosphere, it encounters what engineers call max Q, the point where the combination of air pressure and velocity exerts the greatest mechanical load on the structure. The vehicle shakes, flexes, and groans. Panels vibrate, seals stretch, bolts experience tons of tension. Every mission must survive those seconds of maximum stress before the atmosphere thins and the forces fade. There's something humbling about the fact that every successful launch, no matter how routine it looks from the ground, flirts with destruction for that brief interval. The balance between thrust, drag, and structure is razor thin. If the engines burn too hot, the vehicle might tear apart. If they underperform, it could fall back. The price of acceleration is precision, and precision is hard won. In recent decades, engineers have begun to reclaim some of that cost. Reusable rockets, once thought impossible, are now landing back on Earth, descending through the same air they once conquered, guided by computers and thrusters to settle upright on narrow pads. The first time a booster returned safely from orbit, it felt almost magical, like watching gravity and technology strike a temporary truce. But behind the spectacle was pure mathematics. Reusability doesn't just save hardware, it saves energy, material, and time. It allows us to invest the price of acceleration once, then reuse it again and again. Still, the fundamental equation remains the same. Chemical rockets, no matter how refined, are limited by their exhaust velocity, typically a few kilometers per second. The energy density of chemical fuels is finite. No matter how efficient we become, there's a ceiling to how much speed we can buy with chemistry alone. That's why every discussion of future propulsion, from ion engines to nuclear thermal rockets, begins with the same question: how do we accelerate more without burning everything we carry? The gentle push. The ion drive offers one answer. Instead of explosive bursts of thrust, it uses electricity to accelerate charged particles, ions, out of the engine at extremely high speed. The thrust is tiny, often less than the weight of a sheet of paper, but it can run continuously for months or years. Over time, that gentle push accumulates into extraordinary velocity. It's not practical for lifting off from Earth, but once in space, it's unmatched for efficiency. The Deep Space One and Dawn missions both used ion propulsion to visit multiple asteroids and planets with minimal fuel. Their success proved that slow acceleration can be more powerful than brute force. There's something elegant about that idea, trading intensity for endurance, power for patience. It mirrors how much of the cosmos itself operates. Stars burn steadily for billions of years rather than in brief bursts. Orbits persist because of balance, not strength. The universe, in its quiet way, rewards consistency over violence. Ion engines follow that same logic. They pay the price of acceleration slowly, in installments rather than all at once. But for humans, that patience has limits. Crew missions require quick departures and short travel times. You can't drift for years on a whisper of thrust if you're carrying people, supplies, and life support systems. For now, the only practical way to leave Earth remains the chemical rocket. Loud, powerful, fleeting. Every launch is a reminder that acceleration still costs us dearly. That cost is also emotional. Watching a rocket rise, knowing how fragile it is and how much it carries, stirs something deep in us. It's the visible expression of humanity's hunger to move faster, to see farther. Each launch is both triumph and risk, a gamble we take because the reward, discovery, knowledge, perspective feels worth it. When the engines finally shut down and the spacecraft settles into its planned trajectory, there's a sense of relief, but also reflection. The violence is over. The momentum has been earned. The rocket has done its job, and now the universe takes over. The same laws that demanded such an enormous price for acceleration will now grant endless silent motion in return. In that exchange lies the quiet fairness of physics. Some engineers like to say that space begins where airplanes stop making sense. That's not just about altitude, it's about method. Airplanes generate lift by pushing against air. Rockets create motion by pushing against themselves. That's why they're so costly. There's no external surface to lean on, no medium to borrow energy from. Every bit of thrust must come from inside. Every second of acceleration bought with mass turned to exhaust. It's a strange irony that the emptier space is, the harder it is to move through. The vacuum offers no resistance, but also no assistance. Motion there is pure, no drag, no turbulence. But getting there requires a kind of sacrifice. The rocket must shed its weight, its fuel, its stages, even parts of itself until only the essentials remain. The process is destructive by design, and yet it's the only way to reach the calm that follows. In that sense, rockets are a reflection of human ambition itself. They start heavy, loud, and bound by gravity. They struggle, shed what's unnecessary, and eventually find a steady path through the void. Every launch is a metaphor for growth, disguised as engineering. We spend vast resources to gain freedom, and once we have it, We drift quietly, weightless, realizing how small we still are. As technology advances, we're finding ways to make that process gentler. Reusable boosters touch down softly instead of crashing into the ocean. New fuels burn cleaner. Autonomous guidance reduces the risk of human error. Each improvement trims a little from the price we pay to move upward. But no matter how refined our designs become, acceleration will always cost something. Energy, time, patience, and awe. Because acceleration is more than motion, it's transformation. It's the act of changing states, from rest to movement, from Earth to orbit, from silence to sound and back again. Every rocket embodies that change in physical form, a vessel that carries us from what we know into what we can only imagine. And as the engines fade and the spacecraft drifts into the dark, the story of acceleration gives way to the story of exploration. The question shifts from how to leave Earth to how to keep moving once we're free. In that quiet, where fuel runs low and momentum becomes everything, we begin to learn that the real art of traveling space isn't just about how fast we go, but how we use the speed we've earned. The price of acceleration, after all, isn't just paid in energy, it's paid in perspective. Every time we leave the ground, we see our world more clearly. A small blue sphere that demanded everything we had just to escape, yet still calls us back with every orbit. And somewhere out there, past the noise and the heat, we find the beginning of what it truly means to move among the stars. The race beyond the sky. The moment humanity learned to leave the atmosphere, something shifted forever. For most of history, the sky was an unreachable ceiling, a bright and distant boundary where clouds drifted and stars watched silently from above. Then, in the middle of the 20th century, that boundary cracked open. The air itself was no longer the limit. A few machines, fragile and blazing with fire, began to climb beyond blue and into black. What followed was not just exploration, it was a race. One that began in fear, matured in awe, and ended in a quiet understanding of what it means to move beyond the world that built us. The early decades of spaceflight were not born from calm curiosity, but from tension. The Cold War was at its height, two nations watching each other through the lens of suspicion and ambition. Science and politics intertwined in ways that shaped everything about how fast humanity would learn to travel. In October of 1957, when the Soviet Union launched Sputnik 1, the world changed in a single beep. That simple radio signal, transmitted from a small metal sphere barely the size of a beach ball, circled the Earth every 96 minutes. Its message was minimal, just a rhythmic pulse, but it was enough. The sound told everyone on Earth that the sky was no longer empty. That little satellite was moving at almost 18,000 miles per hour, faster than anything humans had ever built. For the first time, a human-made object was circling the planet, not falling back, not failing, simply staying. The realization rippled through the world like a shockwave. The Soviet Union had beaten the United States to space. They had proven they could launch something fast enough, powerful enough to orbit the Earth. And if they could launch a satellite, they could, in theory, launch anything. The race beyond the sky had begun. In the years that followed, every milestone became a contest. The first animal in orbit, the first man, the first woman. Each success carried both scientific triumph and geopolitical weight. But beneath the rivalry, something else was growing, a sense of collective wonder. Speed had turned into symbolism. The faster we could go, the farther we could dream. In April 1961, Yuri Gagarin climbed into a spacecraft called Vostok 1. It was small, barely room for one person, more like a metal sphere than a capsule. At the top of a rocket, nearly 100 feet tall, He waited while thousands of tons of propellant trembled below him. When the engines ignited, they lifted him through layers of atmosphere, past the point where blue turns to black, into orbit. He completed one full circuit of Earth in 1 hour and 48 minutes, traveling at nearly 5 miles per second. His call sign during launch was Cedar, meaning Siberian pine, and his calm voice over the radio became a kind of reassurance that humanity had finally left the cradle. When he returned, the world erupted in celebration. It wasn't just a Soviet victory, it was a human one. A person had circled the planet, seen the curve of the horizon, and returned alive. Gagarin's words, simple and soft, carried a resonance that outlasted any political speech. "I see Earth. It is so beautiful." Not long after, another flight followed, this time from the United States. Alan Shepard's Freedom 7 flight reached space just a few weeks later. Though it didn't complete a full orbit, still it proved that America was catching up. Then came John Glenn, who orbited Earth 3 times in 1962, and Valentina Tereshkova, who became the first woman in space in 1963. The race was accelerating, both nations learning with every launch, pushing technology to its edge. Behind each of these flights was an army of engineers, mathematicians and scientists who were rewriting the rules of motion. Computers at the time filled entire rooms, their memory measured in kilobytes, yet they guided trajectories that had to be accurate to within fractions of a degree. Propellants were refined, materials strengthened, and telemetry systems improved. Each failure taught something new. Rockets exploded, capsules malfunctioned, and astronauts risked their lives every time they climbed into those cramped high-speed machines. The speeds they reached were astonishing, nearly 17,000 miles per hour for orbital flight, and later, as missions reached for the moon, even higher. But what truly mattered wasn't the raw velocity, it was the realization that humans could master it. We had entered an environment where speed was no longer a luxury but a necessity. In orbit, if you go too slow, you fall, too fast, and you drift away forever. The race wasn't about who could build the fastest machine, it was about who could live in perfect balance with motion itself. When President John F. Kennedy stood before Congress in 1961 and declared that America would land a man on the moon and return him safely before the decade's end, it sounded impossible. The distance was enormous, the technology untested, yet the challenge ignited something beyond competition. It gave purpose to the pursuit of speed. No longer was it only about beating an opponent, it became about proving that humans could go beyond Earth entirely. The Apollo program was born from that promise, and with it came some of the most powerful machines ever built. The Saturn V rocket stood taller than a 30-story building and could generate 7.6 million pounds of thrust. Fully fueled, it weighed over 3,000 tons. When it launched, the ground shook miles away. It was as if the planet itself were helping it leave. Each stage fired in sequence, adding more and more speed until the spacecraft reached over 7 miles per second, fast enough to escape Earth's gravity. The astronauts who rode those rockets became the fastest humans in history. During re-entry, as they fell back toward Earth, their capsules reached speeds exceeding 24,000 miles per hour. No person before or since has moved faster relative to the planet's surface. That speed was not an abstraction. It was the difference between success and tragedy, between orbit and open space, between life and silence. In July 1969, when Apollo 11 touched down on the moon, the race that had begun with a beeping sphere 12 years earlier reached its quiet conclusion. Neil Armstrong and Buzz Aldrin stepped onto another world, moving slowly in the low gravity, their every motion deliberate. The contrast was poetic. After years of chasing velocity, Humanity's greatest achievement in speed ended in a moment of stillness, a footprint pressed into dust that had never known motion before. That moment reshaped how we thought about travel. The race beyond the sky had begun with rivalry, but ended with perspective. The sight of Earth hanging in the blackness, small, delicate, luminous, changed everything. The astronauts described it as a revelation. From that distance, there were no borders, no rival nations, just one world suspended in darkness. The true destination, they realized, wasn't the moon. It was understanding our own place in motion. After Apollo, the intensity of the race slowed, the political urgency faded, but the momentum of discovery continued. The focus shifted from speed to endurance, from how fast we could reach space to how long we could stay there. The space shuttle era began in 1981, turning spaceflight from one-way missions into something reusable and routine. The shuttles were slower than lunar craft, but more sustainable. They orbited Earth at about 17,000 miles per hour, carrying crews of up to 7 people. They delivered satellites, built the International Space Station, and taught us how to live and work in microgravity. Even as speed became less of a headline, the achievements of that period deepened our understanding of acceleration and re-entry. Engineers developed better heat shields, more precise guidance systems, and reusable engines that could withstand repeated launches. The race was no longer about who could go fastest, but who could go smartest, who could make speed sustainable. Beyond human missions, robotic explorers carried the torch of acceleration. Probes like Pioneer, Voyager, and later New Horizons achieved speeds no crewed craft could match. They were light, durable, and tireless. Voyager 1, launched in 1977, used the gravitational pull of giant planets like Jupiter and Saturn to slingshot itself toward the outer reaches of the solar system. Each encounter added speed without using additional fuel, a maneuver known as a gravity assist. By borrowing momentum from planets, Voyager 1 eventually reached over 10 miles per second relative to the Sun. That speed, achieved decades ago, still carries it farther every second. It has now crossed into interstellar space, still whispering data back to Earth across billions of miles. That technique, using gravity itself as an engine, became one of the most elegant discoveries in the history of travel. Instead of fighting nature, we learned to collaborate with it. A spacecraft could dive close to a planet, let its gravity pull it in, then swing around and use that pull to accelerate outward. The planet's orbit slows by an imperceptible fraction, but the spacecraft gains enormous speed. It's a trade invisible to the eye, yet capable of propelling machines to the edge of the solar system. The race beyond the sky, then, was never truly about rivalry. It was about learning how to move in harmony with the forces that govern motion itself. Gravity, thrust, inertia, time, all of them part of the same quiet conversation between matter and energy. Every launch, every orbit, every flyby is a sentence in that ongoing dialogue. When we talk about the fastest speeds in space, we usually think of numbers, thousands of miles per hour, fractions of light speed. But there's another kind of speed that emerged from that era, the speed of understanding. What took nature billions of years to create, stars, planets, orbits, we began to grasp within a few generations. That leap in knowledge was its own form of acceleration. We learned not just how to move through the universe, but how to think within its terms. And even as the race cooled, the dream persisted. Every new mission carried within it the same question that launched the first. How far? How fast? How much closer to the stars can we reach? New nations joined, private companies emerged, and what was once a duel between superpowers became a shared pursuit. Now, as reusable rockets rise and land with machine-like precision, as probes skim the edge of the sun, As telescopes peer deeper into time itself, the race beyond the sky continues, quieter, steadier, but still burning with the same desire to move forward. The next frontier is no longer a contest, but a collaboration. It's a slow unfolding of possibility. Humans and machines learning how to share the velocity of space without losing the calm of purpose. The distances remain vast, the physics unchanged, the costs immense, but the fear that once fueled the race has softened into wonder. We no longer look up to challenge the sky, we look up to understand it. The speed that once divided us has become the speed that connects us. Satellites orbiting at thousands of miles per hour link voices across continents, guide ships through oceans, and map the surface of the world in real time. The very instruments of rivalry have become the infrastructure of unity. In that sense, the race beyond the sky never truly ended. It simply changed direction, from competition outward to collaboration inward. Every time a new rocket launches now, there's still a flicker of that old thrill. The engines ignite. The countdown echoes, and for a moment humanity remembers what it feels like to defy gravity together. The numbers, the speed, the altitude still matter, but they're no longer the story's heart. The real wonder is that we can do it at all, that we can take something as heavy as hope, fill it with fire, and watch it rise into the endless dark. And as the rocket disappears from sight, its flame fading to a pinprick against the sky, we're reminded that speed isn't the opposite of stillness. It's another way of reaching it. The faster we go, the more distant Earth becomes, and the more clearly we can see it. From orbit, from the moon, from the edges of the solar system, everything else slows down. The race beyond the sky, it turns out, was never just about getting there first. It was about learning what it means to move at all, to measure distance not in kilometers, but in understanding. The machines that now drift beyond the edges of our solar system began as sparks of imagination, born in laboratories and workshops where people dared to think about speed not as a limit, but as an invitation. Our swiftest machines. Each one was built to go faster than anything before it, to turn the dream of motion into a tangible path across the stars. These are the swiftest machines we've ever built, human creations that have reached velocities our ancestors could not have even imagined, yet all of them powered by the same quiet physics that govern a falling apple or a spinning planet. The story of these machines begins in the decades after humanity first learned to escape Earth. Once we knew how to leave, the question shifted from if to how far. Rockets had taken people into orbit, to the moon and back, but machines could go farther, faster, and endure for years where no life could survive. They didn't need air, comfort, or return tickets. They only needed precision, patience, and enough momentum to carry them through silence. One of the earliest and most enduring of these travelers was Voyager 1, launched in 1977. It was designed to study the outer planets, Jupiter, Saturn, and their moons. The spacecraft itself wasn't large, only about the size of a small car, but its purpose was monumental. It carried instruments to measure magnetic fields, radiation, and the composition of distant worlds, along with a record, a golden disc engraved with sounds and images of Earth, a message for anyone who might someday find it. The mission planners used a rare planetary alignment that happens only once every 176 years. By timing the launch correctly, Voyager 1 could use the gravitational pull of each giant planet to accelerate, a maneuver known as a gravity assist. As it passed close to Jupiter, it fell toward the planet's immense gravity well, gained speed, and then swung away, stealing a fraction of the planet's orbital energy. It repeated the process at Saturn, accelerating again, without burning more fuel, It was flung outward at an ever-increasing rate until it was moving at over 10 miles per second relative to the Sun. That speed, about 38,000 miles per hour, is hard to imagine. It means Voyager 1 travels the distance from New York to Los Angeles in less than 4 minutes. Yet even at that astonishing pace, the scale of the universe dwarfs it. It took 35 years for the spacecraft to reach the edge of the Sun's influence, a region known as the heliopause. In 2012, it crossed into interstellar space, where the solar wind fades and the environment becomes the domain of distant stars. It remains there now, more than 15 billion miles away, still transmitting faint signals to Earth. Its twin, Voyager 2, launched a few weeks earlier, followed a different path. It visited Jupiter, Saturn, Uranus, and Neptune, the only spacecraft ever to visit all 4 giant planets. Each encounter added to its velocity, pushing it outward into the same eternal drift. The Voyager's speed wasn't a product of raw engine power, but of clever timing and the gravitational generosity of the planets themselves. It showed that speed in space doesn't always come from strength. Sometimes it comes from understanding the rhythm of celestial motion. After the Voyagers came New Horizons, a mission with a destination that once seemed unreachable, Pluto. Launched in 2006, it became the fastest object ever to leave Earth at the time, departing at nearly 36,000 miles per hour. Its journey to Pluto took 9.5 years, covering more than 3 billion miles. During that time, it hibernated in deep space, waking periodically to check its systems before resuming its silent flight. When it finally arrived in 2015, it passed within 7,500 miles of Pluto's surface, capturing images that revealed mountains of ice, frozen plains, and hints of an atmosphere shimmering in faint sunlight. Then it continued on, past Pluto's orbit and deeper into the Kuiper Belt, where it encountered another small world, Arrokoth. Each maneuver carried it farther and faster, powered not by engines, but by the inertia gathered at launch. Even greater speeds were achieved closer to home. The Parker Solar Probe, launched in 2018, was designed to study the Sun, not from afar, but up close, closer than any spacecraft before it. To do that, it had to perform the opposite of what most missions attempt. Instead of accelerating away from the Sun, it needed to slow down relative to it, which meant falling inward, trading altitude for velocity. Each orbit around the Sun brought it closer, and as it descended, gravity took over. By 2024, Parker had reached speeds of about 430,000 miles per hour relative to the Sun. That's fast enough to travel from Earth to the Moon in less than an hour. To survive such proximity, it carries a heat shield that withstands temperatures over 500 degrees Fahrenheit, protecting instruments that operate in the shadow behind it. In the void between orbits, the spacecraft glides silently, its instruments measuring solar winds and magnetic fields, while moving faster than any human-made object in history. Speed in space, however, is a strange concept. It depends entirely on what you compare it to. Parker Solar Probe is the fastest relative to the Sun, but other spacecraft have reached higher speeds relative to Earth or other bodies. The Helios probes of the 1970s, also sent to study the Sun, reached over 150,000 miles per hour in their elliptical orbits. The Juno spacecraft, currently orbiting Jupiter, achieved more than 160,000 miles per hour during its closest approach to the planet, pulled by the gas giant's immense gravity. These speeds sound immense, but what's most remarkable is how steady they are. In the vacuum of space, once acceleration stops, nothing slows you down. There's no air resistance, no friction, no drag. The spacecraft will keep moving forever, or until gravity alters its course. That's why many of these machines will outlive their creators. their speed will carry them onward through centuries, their paths unchanged except by the faint tugs of distant stars. It's humbling to think that the fastest things we've ever built are now beyond our sight, yet still connected to us by the narrow thread of radio waves. Each one transmits data across billions of miles, and though the signals weaken, they persist. Voyager 1's current messages take more than 22 hours to reach Earth, traveling at the speed of light. That means when we receive its data, it's already a record of the past, a delayed echo of a machine still racing through space at unimaginable speed. These machines have redefined how we understand motion. They've shown that speed is not only a measure of distance over time, but also of endurance over silence. A car, a plane, or even a rocket can only sustain speed for minutes or hours. These spacecraft have maintained it for decades. Their engines have long been shut off, yet they remain in motion, not slowing, not fading, simply moving forward through the endless dark. It's also a reminder that the word fast is always relative. Even at hundreds of thousands of miles per hour, these machines are crawling compared to light, which travels nearly 186,000 miles every second. At that rate, light from the sun reaches Earth in just over 8 minutes. The Parker Solar Probe, the fastest machine ever built, would take over a month to cover that same distance. That gap between the attainable and the ultimate defines the boundary of our current technology. Yet within that boundary, there's beauty and precision. To achieve these velocities requires extraordinary accuracy. Every trajectory, every burn, every gravitational flyby must be calculated to within meters, even when traveling billions of miles. A small miscalculation at the start could mean missing a planet by millions of miles. Navigation in space is a discipline of patience. Engineers track the faint signals from deep space antennas, measure Doppler shifts in frequency to detect changes in velocity, and adjust accordingly with gentle course corrections. The smallest nudge can mean success or failure, but every successful adjustment is proof that we can control motion across interplanetary scales. The machines that achieve these feats are not large, but they are profound. Each one carries the weight of human curiosity wrapped in metal and circuitry. They don't experience speed the way we do. There's no sensation, no wind, no vibration, yet their movement tells a story of persistence. They embody the idea that once set in motion, a human creation can continue to explore long after its makers are gone. The instruments aboard these spacecraft are small miracles in themselves. The cameras that captured the first close-up images of Jupiter's storms, the magnetometers that traced invisible fields through space, the sensors that felt the particles of solar wind. All of them are extensions of human perception. They transform speed into knowledge. The faster they move, the more they encounter, and the more they send home. Even today, new generations of spacecraft are being designed to break existing records. Concepts for solar sails, which use the pressure of sunlight itself to accelerate, could one day achieve continuous speed increases without fuel. Projects like Breakthrough Starshot imagine gram-scale probes propelled by lasers, accelerating to a fraction of light speed to reach nearby stars within decades instead of millennia. The energy requirements are staggering, but the principle is sound: acceleration through light, speed through patience. Each of these efforts traces its lineage back to the same question that once inspired the first rockets: how fast can we go, and what does that mean for where we can reach? The answer so far has always been the same: faster than before, but never fast enough to touch the limits of imagination. If you think of speed as an expression of intent, then these machines are our most honest reflection. They are humanity's will to move turned into metal. They show that even when we can't follow in person, we can send our curiosity ahead, let it travel where our bodies cannot. and in that way we're already explorers far beyond our own reach. The swiftest machines we've ever built are not just records of velocity, they're records of endurance, of how long we can maintain focus, how far we can sustain attention. They remind us that progress in speed is not only measured by how fast we move, but by how long we continue to care about what we've set in motion. The Voyagers are still transmitting because people on Earth are still listening. The signals are faint, delayed, and fragile, but they persist because curiosity hasn't stopped. And as those signals travel through the void, their journey continues on two levels, one physical, one symbolic. Physically, they move at tens of thousands of miles per hour, drifting farther from the sun with every passing second. Symbolically, they carry the memory of what it took to make them, the years of work, the generations of thought. In their speed, we can see the trajectory of human thought itself, a steady acceleration that shows no sign of slowing. When you look at the sky tonight, you won't see them. They're too far, too faint, too quiet. But they're there, still moving, still representing the farthest edge of what we can currently achieve. They're proof that speed in space isn't about breaking limits, but about extending patience. It's not a sprint, it's a drift that lasts lifetimes. Somewhere between the Earth and the outer dark, these machines continue to coast, the sunlight fading behind them, the stars ahead waiting in silence. Their velocity will outlive our species if we vanish tomorrow. That's the paradox of speed in space. The faster we move, the longer it takes to arrive anywhere meaningful. The distances stretch endlessly. The numbers become abstract, but the motion remains real. And through that motion we continue to learn. Each new mission refines the next. Each record broken becomes the foundation for another. The swiftest machines we've ever built are also the slowest teachers, delivering lessons that take decades to arrive. But when they do, they remind us that every second of acceleration was worth it. Every meter per second gained has given us not only distance but understanding, the kind that expands quietly, like the universe itself. As we move forward, those lessons guide the designs of future explorers, faster probes, lighter materials, smarter propulsion. The pursuit continues, not for competition, but for connection, to see how far we can stretch the reach of thought, to test how long motion can last without fading. The swiftest machines we've ever built are already part of that experiment, still teaching us what speed means when measured not in moments but in eternity. And somewhere in their endless flight, in the space between numbers and silence, lies the quiet truth that has followed every mission since the first. Speed is never the destination. It's the medium that carries us toward everything we have yet to know. Thank you so much for joining me on this journey through the cosmos tonight. If you found peace in these thoughts, if the exploration of speed and silence resonated with you, I'd be incredibly grateful if you'd take a moment to like this video. It truly helps more people find this quiet corner of wonder. And if you'd like to continue exploring